Hi, everyone. Today we are looking at the gas turbine cycle. So the first part of it, we will be looking at simple gas turbine cycle. So before that, okay, let us take a look at the terms that we use in this chapter or in thermodynamics. So in thermodynamics and engineering, a heat engine. So by now you should know what is a heat engine. Is a system that converts heat energy to mechanical energy. So most of the gas cycles that we have done, or even the power plant, the vapor power plant, it actually converts heat energy to mechanical energy, such as work done, potential energy, or kinetic energy. Now, which can then be used to do mechanical work. So it converts mechanical work, okay, to power or to electrical power by means of a generator or an alternator in certain heat engines. So an internal combustion engine. So this chapter, that is gas turbine engine, is also being called or is also being known as an internal combustion engine. Is a heat engine in which the combustion or the burning of the fuel occurs with air in a combustion chamber. So in internal combustion engine, the burning of fuel takes place inside, okay, inside the system, okay, so within. But then if let's say external combustion engine such as steam engine, the combustion or the burning of fuel is taken place outside of the engine, outside of the engine. So that is the difference between internal combustion and external combustion engine. Okay, so it's a heat engine in which the combustion or the burning of a fuel occurs with air in a combustion chamber. So the chamber which burning, okay, is taking place, okay, or a space which, okay, you have burning. Now in an internal combustion engine, the expansion of the high temperature and pressure gases produced by the combustion applies direct force to some components of the engine. So the next term is the turbine, which is a rotary mechanical device that extracts energy from fluid flow and converts it into useful work, especially kinetic energy, into work. So the work produced by a turbine can be used for generating electrical power when combined with a generator. So this is an example or a diagram which I have taken from Wiki. Okay, so this is a jet engine. So you look at this diagram here, you have intake, then you have compression, then you have combustion, that where burning takes place. Okay, and then after that you have the exhaust, hot gases, okay, at high speed. Intake usually is done by a compressor, okay, so it sucks in air from the surrounding, okay, from the surroundings, and it will be at surrounding or the ambient temperature or the atmospheric temperature and pressure. So then what happens as it is, what happened here is the air is being compressed, okay, being compressed, then with the help of fuel that is being injected to the burning section, what happened is the air and fuel mixture will burn, and then this hot gas will be discharged as an exhaust, which is used to drive propeller or fan and etc. etc. So it gives us a very large momentum. So a jet is a stream of fluid that is projected into the surrounding medium, usually from some kind of a nozzle. By now, you should know what is a nozzle, which you have done in your fluid mechanics. Now, a jet engine is a type of reaction engine discharging a fast-moving jet that generates thrust by jet propulsion. Now, an air-breathing jet engine is a jet engine that emits a jet of hot exhaust gases formed from air that is forced into the engine by several stages of centrifugal, axial, and compression, which is then heated and expanded through the nozzle here. So a propelling nozzle is a nozzle that converts the internal energy, by now you should know what is internal energy, of a working gas into propulsive force. Okay, so these are the terms that usually you will see in this chapter, in this section. So the turbojet is an air-breathing jet engine typically used in aircraft. It consists of a gas turbine, this is what we are looking at now, okay, with a propelling nozzle. Now the gas turbine has an air inlet, a compressor or a combustion chamber or a combustor. We can also call it as a combustor, and a turbine that drives the compressor. The turbine work output actually in return is used to drive a compressor or drive the compressor. So the network output must be greater than the work input. So the compressed air from the compressor is heated by burning fuel in the combustion chamber and then allowed to expand through the turbine. Okay, so the turbine exhaust is then expanded in the propelling nozzle, where it is accelerated to high speed to provide thrust from this part here. And this section here is called the hot section. This part is called the cold section. So a gas turbine is a type of internal combustion engine. Okay, so by now you should know what is internal combustion engine now. Now the main elements or devices of gas turbine engines are first an air compressor or a gas compressor, then a combustor which is used to burn the air and fuel mixture. Here the compressor is used to suck air from the surrounding or from the atmosphere and then compress it to high pressure and high temperature. So when it reaches the combustor, the fuel and air mixture is burned, and energy is produced. Now a turbine is to extract the heat energy that is within the gas, and then it drives the compressor and also a generator if a generator is attached to it to convert to electrical or to convert to axial thrust or especially electrical energy or power. The fourth component is often used to increase efficiency on turboprops and turbofans to convert power into mechanical turboprops. Here they use turboprop or turbofans to convert mechanical or electrical form of energy. So a turboprop engine is a turbine engine that drives an aircraft propeller. So the basic operation of the gas turbine is called a Brayton cycle with air as the working fluid. So basically it starts with Brayton cycle. Now atmospheric air flows through the compressor, brings it to higher pressure and also at higher temperature. So energy is then added by spraying fuel into the air and igniting it, burning it, so that the combustion generates a high temperature flow of gas. Then this high temperature pressurized gas enters a turbine, producing a shaft work output in the process used to drive the compressor, the unused energy comes out in the exhaust gases that can be repurposed for external work, such as directly producing thrust in a turbojet engine, or rotating a second independent turbine known as a power turbine, which we will be dealing very soon. That can be connected to a fan, propeller, or electrical generator. So basically, we will be looking into the analysis or the calculation part of the gas turbine cycle in the next slides. Okay. So the fourth step of a Brayton cycle, that is cooling of the working fluid, is omitted. In a Brayton cycle, you have four processes. Okay, A is sucked in through a compressor. Then A and fuel mixture is burned in a combustor or a combustion chamber. Then work is extracted, okay, from the turbine. And then after that, it will undergoes a cooling to cool down the A. Okay, so if let's say, for example, in gas turbine, you cannot recycle the gas because suction is A, exhaust is gas. So you cannot mix it. So usually jet engines are open cycle and Brayton cycle is a closed cycle. So closed cycle means then they cannot use a combustor. Instead of a combustor, they use a heater, and then they also use a cooler. The heater to raise up the temperature, cooler is to reduce the temperature. So for Brayton cycle, so Brayton cycle is a closed gas turbine unit cycle. Okay. So the fourth step of Brayton cycle have a fourth step. Gas turbine cycle only 3 steps. So cooling of the working fluid is omitted in gas turbine cycle. Okay, as gas turbine cycle are open system that do not reuse the same A. Gas turbine are used to power aircraft, trains, ships, electrical generators, pumps, and gas compressors. So in an ideal gas turbine, okay, gases undergo 4 thermodynamic processes. That is, which we have done earlier, which we call it as constant pressure cycle in the earlier part of gas cycles, which we call it as constant pressure cycle. They have 4 thermodynamic processes. First is the constant entropy or isentropic compression. Then you have the constant pressure or isobaric combustion and isentropic expansion, okay, and heat rejection. Together, this makes up the Brayton cycle. That is for Brayton cycle, not the open gas turbine unit. It is for a closed gas turbine unit. So the first, the gas turbine power. So open gas turbine unit. Now fresh air at ambient conditions, okay, surroundings, is drawn into the compressor where its temperature and pressure are raised. The high pressure A proceeds into the combustor or combustion chamber where the fuel is burned at constant pressure. Now resulting high temperature gases enters the turbine where they expand to the atmospheric pressure. That means they discharge it directly to the atmosphere while producing power. Now the exhaust gases leaving the turbine are thrown out, not recirculated, causing the cycle to be classified as an open cycle. So this is the example. This is a drawing that I have done. So basically, when you look at this, okay, you have 3 devices. First is a compressor. Second is the combustor or the combustion chamber. Third is the gas turbine. So compressor, gas turbine, both undergoes isentropic processes. So the compressor will undergo isentropic compression. Gas turbine will undergo isentropic expansion, where work is extracted to move okay, or to propel a propeller or a fan, or using a generator to convert it to electrical energy. So combustor or the combustion chamber will work at constant pressure where the heat energy is generated and the temperature is increased. Initially in the compressor, the pump and the temperature also increase when it undergoes isentropic compression. The temperature and pressure do increase when it undergoes the compressor. When the air is sucked in from the atmosphere or the surrounding, and then it undergoes number of stages where the pressure and temperature is brought up, and then it will be directed to the combustor where it mixes with fuel. Okay, due to high pressure and high temperature, the mixture will be burnt, ignite. The ignition will take place, and hence it produces hot gases. So you see, inlet is air, outlet is gas. So you cannot mix this and send it back or redirect it back to the compressor where the compressor only take in fresh air from the atmosphere. So this hot gas, okay, will goes into gas turbine where it undergoes isentropic expansion, where it will undergoes isentropic expansion and work, okay, or mechanical energy is extracted to move some other components. And then the remainder, that means the energy which cannot be converted to useful work here, will have to go to the atmosphere. So the discharge, maybe these hot gases on due to recycle energy or due to global warming effect. It is not advised to discharge these hot gases directly to the air. It causes global warming effect. So most of the time, people nowadays will do something with this part here, where it is used to some other works, maybe rotating or doing some other works. Okay, that will be discussed in later parts. Okay, or usually combined with steam power, okay, to heat up, okay, the saturated liquid before it's sent to the boiler. Okay, so most of the time, this gas turbine cycle is combined with other cycles, so that this hot gas will not be directly discharged to the atmosphere at high pressure, high temperature. Okay, which is a waste, one thing. Second thing, it will causes global warming effect. Okay, so that is the simple gas turbine unit. This is a simple gas turbine unit. Okay, so state point 1 to 2 from here to here undergoes isentropic compression. By now, you should know what is isentropic. This is constant entropy compression. So usually here we don't include or we exclude the heat transfer. It's isentropic. Okay, state point 2 to 3 from here to here, it undergoes a constant pressure heating process. When this takes place, the mixture of air and fuel or gas. Okay, so burning takes place, and then it produces, okay, energy, heat energy. So then the third point, the third process is from state point 3 to state point 4, where the system or the substance, okay, or the working fluid will undergoes isentropic expansion. Again, I repeat, isentropic means constant entropy, no heat flow involved. Okay. So this will be the TS diagram for the open gas turbine unit. This is a constant pressure cycle actually, but from this you can see it's actually open. Okay, we don't include this part usually when we draw the TS diagram. Okay, so I just wanted to show you the difference between a closed cycle. So closed cycle, for Brayton cycle, it usually 1 and then to 2 and then 0.3 and then to 0.4 and then back to 0.1. That is a closed gas turbine unit. That is the Brayton cycle, where 1 to 2 it undergoes isentropic compression, then constant pressure heating, then isentropic expansion, then constant pressure cooling back to state point 1. Now, if let's say, for example, we are looking at gas turbine unit, it will start at 0.1 and then it will go through an irreversible compression, to state point 2 prime. This is due to internal frictions. Okay, internal friction. But now you should know what it means by internal friction, and it causes a certain amount of irreversibilities. So usually irreversible process, we use dashed line here to represent it. Okay, so solid line we usually refers to reversible, dashed line we usually refers to irreversible. Now, so this is due to the irreversibilities of the energy, okay, because due to internal friction. So from there it will go from state point 2 prime to state point 3, where it undergoes constant pressure heat addition. In actual cases or in real practice, okay, usually we have pressure drop, but then for our level, we only look at things that without pressure drop. So that means we neglect any pressure drop. Okay, then when you go for higher level, then you will have to include pressure drops from state point 2 prime to 3. So from state point 3 to state point 4 prime, then, okay, it undergoes irreversible expansion process. That is also due to certain amount of irreversibilities. And from this state point 3 to 4 prime and 1 to 2 prime, later on we will have a term called the isentropic efficiencies. The isentropic efficiencies will be defined. So it stopped at 0.4 prime, and then the hot gases will be exhausted. Okay, for our studies it will be exhausted to the surroundings. Okay, because we are not looking at combined power cycle yet. So that is how the actual cycles move for the open gas turbine unit. So it goes from 1 to 2 prime, 2 prime to 3, and from 3 to 4 prime. So the isentropic efficiency is due to the irreversibilities. We have this term here which we call the isentropic efficiency. We have for compressor, this part is the compressor part, and this turbine part. So the isentropic efficiency for the compressor actually is defined as the theoretical work input divided by actual work input. I repeat, theoretical input divided by actual work input. Now, so compressor is dealing with air. So usually is written as CPA, which CP stands for specific heat capacity at constant pressure. If I write CPA, that means it represents specific heat capacity at constant pressure for A. So you will have CPA T2 minus T1 divided by CPA T2 prime minus T1. Since the numerator and the denominator has the common CPA, so that is why you don't see a CPA written in the formula. So it's directly written as in terms of temperature only, where the CPA is being neglected. So for standard case, the specific capacity at constant pressure for A is taken as constant, which is equal to 1.005 kilojoules per kg K. So since they are the same, so that is why we neglect. We strike off the CPA. So what we have is this formula here for the compressor. I repeat once more, is defined as the theoretical work input divided by the actual work input. Or usually how I remember this is by taking the out divided by the in. Means the outside of the diagram divided by the inside of the diagram. The temperature difference is the outside divided by the inside. So therefore, it is easier for us to remember, because since we are remembering too many formulas. Okay, so this is the A intake temperature. So in order to find T2 from this process, we usually take isentropic. Isentropic means you are referring to the vertical line, not the dashed line. Okay, the dashed line is not isentropic process. Okay? It's an irreversible process. So the isentropic process only refers to state point 1 to 2. So with 2, we can use the isentropic relationship between PVT. We can find out the temperature T2 if, let's say, the pressure ratios are given. Usually they have given us the pressure ratio for open gas turbine unit. And gamma usually is taken as a constant for A, which is equals to 1.4. So once you have got T2, then you can substitute here to find out what is T2 prime. So then you have isentropic expansion, this part for the turbine. So the isentropic efficiency for the turbine, that means the tail, usually I call this as the head and this as tail. So the isentropic efficiency for turbine now is defined as actual over theoretical. This one is as theoretical over actual. This one is defined as actual over theoretical. For the turbine side, now since after the combustion chamber, what we have is gas. Is different from compressor, where the intake and once when it goes through the whole process is still remain as A. But then once we come to the turbine, the tail side, it is already gas. So usually we have CPG and CPG here. For both the actual and the theoretical, we have CPG T3 minus T4 prime, which is the actual work output, divided by the theoretical work input, the theoretical work output, which is CPG T3 minus T4. So remember, CPG will be strike off because both the numerator and the denominator, they are common, so you can strike it off, or you can neglect, or if you want to include, you can do so. So when you look at this, again, this is an isentropic process, so you can use the relationship PVT here to find out T4. So once you know T4, then you will be able to find T4 prime. Then the deviation of actual gas turbine cycles from the ideal ones. Okay, so the actual gas turbine cycle differs from ideal ones due to one, some pressure drop during heating addition and heat rejection process is inevitable. Okay, inevitable. So, but then we are not looking at any pressure drop yet. Okay, so point 2, the actual work input to the compressor is more and the actual work output from the turbine is less because of irreversibilities. Okay, so you have to be careful with this and this. This is theoretical over actual. This is actual over theoretical, or you use my way of remembering things, outside over inside, outside over inside, like this. The outside temperature difference divided by the inside temperature difference. After you have neglected the CPG for the gas turbine side and neglecting the CPA for the compressor side. Now, the deviation of actual compressor and turbine behavior from the ideal isentropic behavior be accurately accounted by utilizing the isentropic efficiencies of the turbine and the compressor. So that is what is given. So this is in terms of H, the enthalpy. And we know that H enthalpy can be written as CPT. Okay, the specific capacity at constant pressure multiplied by the absolute temperature. Okay, so we can convert this into this form also as well. This one into this form. Okay, so if let's say, for example, you are referring to air tables or gas table, you can directly use enthalpy in terms of enthalpy. Otherwise, you have to use this. Okay, usually I advise students to use in terms of temperature. Okay, because sometimes we don't have the proper gas tables or the proper air tables. Okay, so this will be the simplified open gas turbine unit, the schematic diagram. Okay, so based on compressor, again from steady flow energy equation, we work from steady flow, not non-flow, because we are dealing with steady flow devices here. All these are steady flow devices. So isentropic compression now starting from SFEE 1 to 2 prime. So that is how we have written it down. And then remember, isentropic, we neglect heat, we neglect the potential, we neglect the kinetic for pump or compressors. So what we have is the work input, okay, which is CPA. Now, please take note of this. This is CPA and not CPG. The compressor is the A side, remember. Okay, so I have written down, I have explained, or I have specified here what is CPA. For A, the specific capacity at constant pressure for A is standard at 1.005. Sometimes it might be 1.006 or 1.004 or 1.007. Okay, it doesn't make a big difference. So then based on steady flow energy equation, again, the combustion chamber or the combustor is considered the gas side. We don't usually consider it as A side. We usually consider it as gas side. That's what happened inside the combustor. So it is turning to gas. So that is why I say gas side. So the constant pressure heat addition. So again, steady flow. So this time you have heat, but you have no work. So neglect work, neglect potential, neglect the specific change of kinetic energy. So you would have the heat is equals to the change of enthalpy here. Okay, so you can also convert this to CPG, T3 minus T2 prime, since it is gas side. So better take note, this is CPG and this is CPA. Okay. Then a turbine, again based on the steady flow energy equation, isentropic expansion. Okay, so this is your steady flow energy equation. Isentropic, so we don't have heat flow. So this term here can be neglected. So the specific potential energy change and the specific kinetic energy change both can be neglected as well. So then you will have your work output as equals to the change of enthalpy, that is H3 minus H4. So you have this, and remember, this is CPG also. So gas turbine is the gas side also. So the combustor and the gas turbine usually is considered as the gas side. So CPG has different value from CPA. So please take note. If you are referring to an open unit, if you are referring to a closed unit, then you don't have a difference between CPA and CPG. You have CPA the same throughout the whole process if you are using a closed unit. For an open unit, usually we consider A side and gas side. A side and the gas side. So for the gas side, all the gamma that we use, the adiabatic index, also should be referring to the gas. Only for the A, gamma A is 1.4. Gamma for G, it will be stated. Okay, it will be stated. So CPG is the specific capacity constant pressure for gas. So we know, okay, from our knowledge based on heat engine cycles. Okay, net work out, usually we take heat supply and minus heat rejected, but then we don't have a cooler here, or we don't have heat rejected. So that is why the net work out is only measured with respect to work out and work in. So the net work out will be based on work out minus work in, and we know that if we take the difference between these two work, it's also called a net work out. Okay, other than heat supply minus heat rejected, which according to second law. So you have CPG T3 minus T4 prime, that is work out, and work in CPA T2 prime minus T1. Can find both of these, substitute here, and find out the net work out. Then we know heat supply is CPG T3 minus T4 prime. So therefore, we can actually find out the cycle efficiency. The cycle efficiency, which is net work out over heat supply. Or even can find out work ratio. Remember, the definition of work ratio is net work out over the gross work expansion. So when you look at the open gas turbine unit, the only part which give you the gross is all the turbine work. If you have a series of turbines, you must add up all the turbine work to give you the gross expansion. Remember, compressor is compression, so it is excluded from this term. Any compressors, any amount of compressors or any amount of work in will be excluded from this term. Okay, net work out, as I have said or mentioned here, work out minus work in. So therefore, you can find out the work ratio. Okay, so if let's say with the mass flow rate multiplied by net work out, actually you will get the net work out. Or if let's say you take mass flow rate multiplied by heat, then you will have the rate of heat transfer. Rate of heat transfer. Okay, work net multiplied by m dot, which is mass flow rate. You can also have rate of work, which we don't usually call it as rate of work, and we usually call it as power. Now for the closed gas turbine unit, we have seen this in our gas power cycles, not in gas turbine power cycle, in gas cycles, the very first part that we deal. Okay, so which you have compressor, heater, turbine, and cooler. Now both of these is isentropic, and both of these operate under constant pressure. So this is constant pressure heating, constant pressure cooling, isentropic compression, and isentropic expansion. That will give you the Brayton cycle, which is a closed loop. It's different from your open gas turbine unit, which is an open loop. Okay, remember, for open gas turbine unit, you have difference between A side and gas side. For closed gas turbine unit, or constant pressure cycle, we have a common CP throughout. Okay, we cannot have two different type of working substance. So this is a TS diagram which, okay, we have learned from the very first. Okay, so it's complete isentropic and it is a closed cycle. And then this closed cycle here, we can measure heat addition and heat rejection. But for open unit, we are unable to measure the heat rejection because that part is being omitted. Okay. Thank you very much. Okay, that is the end of the first part for the theory. So then after this, we will be going into the calculation part for the simple gas turbine unit. Then only we will move to the more complicated type of gas turbine cycles. Okay, thank you very much for the time being. Hi. So here we will be doing the problem solving for the open gas turbine unit, the simple open gas turbine unit. Okay, so this would be your first example or question 1. So now A gas turbine unit has a pressure ratio of 10:1 and a maximum cycle temperature of 700 degrees C. So they have given us the pressure ratio between the max and the min because you have 10:1. Now, and this would be the highest temperature. So you must add it with 273. So it becomes 973. So the isentropic efficiencies, they have given us the isentropic efficiencies for compressor, which is 0.82. For turbine is 0.85. They want us to calculate the power output of an electric generator geared to the turbine when the A enters the compressor at 15 degrees C at a rate of 15 kg per second. So this would be the mass flow rate. And this would be the inlet temperature. So you have to add it with 273. So it becomes how much? 273, 288. Okay, 288 K. So, and then the second part, they ask us to find the cycle efficiency. And then the third part to be a work ratio. And then they have given us the specific capacity at constant pressure to be 1.005 kJ per kgK. And then the adiabatic index for A is 1.4. The compression process, that means the A side. Then take CPG, that is 1.11 kilojoules per kgK. And the gamma G is 1.333 for the expansion processes. So this would be the gas side. So first, in the question, they have given us pressure ratio 10:1. And then also, the most important thing is they have given us the isentropic efficiency for the compressor, 0.82, and isentropic efficiency for the turbine is 0.85. So this would be the schematic diagram. So you have heat supply here, work in at a compressor, and work out from the gas turbine. So this will be the GAS diagram. So I reminded you here what formula here to use for the compressor side and as well as for the turbine side, the head and the tail. So first thing, now they have given us the first temperature that is 288 Kelvin, that is which is 15 degrees C plus 273. So this temperature here is 288. So this is your temperature axis, and this will be your entropy axis. So here you have temperature 288. So what we need to do is using the isentropic relationship first to find out the T2. So using the isentropic relationship between temperature and pressure, we have known the pressure ratio. They have given us a pressure ratio of 10:1. So that means this will be 10 and here this will be 1. So you have 10:1. So if this is 1 bar, then this will be 10 bar. If this is 1.01 bar, this will be 10.1 bar. Okay? So you have this. So pressure ratio, gamma for A. Remember, compression is the A side, okay? A side. So the gamma should be 1.4. So from this, we will be able to find out T2. So, okay. Then the isentropic efficiency for the compressor. So later you have to remember the formula, okay? But then in these examples, I will be giving you all the formulas here. So the isentropic efficiency for the compressor, why? Because we need to find the T2 prime, because our actual flow path is from 1 to 2 prime, not 1 to 2. 1 to 2 is for closed gas turbine unit. For the open gas turbine unit, you have state point 1 to the state point 2 prime. So what we need to do is to find out the 2 prime here, the T2 prime. So they have given us the isentropic efficiency for compressor, which is 0.82. Okay, so T2, which we have found, 556, T1 which is given 288. So from this we will be able to find our T2 prime, which is 614.83. So on this gas turbine unit cycle, what we need to do is the first thing is find out all the relevant temperatures. All the temperatures will do. Okay. If you are using enthalpy, then you will have to find out all the enthalpies of each of this point here. But then for the gas side, you won't know what type of gas you are using. So you cannot be using a gas table unless they have specified what is the exhaust gas. Okay. So isentropic expansion. Now we come to this part here. Isentropic, the word isentropic, that means we are referring to the vertical line, not the slanting line, okay? Only the vertical line. So isentropic expansion would be 3 and 4, okay? So pressure ratio, again, 10 to 1. So from here, T3 is given in the question. So what we can do is find out T4. So you have this. So T4 would be 547.41. Now all these are your mathematics, yeah? So please, manipulation. So isentropic efficiency of the turbine, that is this. So remember the definition of the isentropic efficiency for turbine and compressor. So compressor, remember, is is theoretical work input divided by actual work input. And for the turbine, is actual work output over theoretical work output. So they have given us 0.85, right? So from this, we will be able to find out the T4 prime, which is 611.25 K. Now the workout, so I have written down the formula. CPG, remember, this is gas side, okay? This is the gas side. So let's take a look at the gamma. You all better double check the gamma that we are using, whether it's correct, which we have used 1.333 or not, okay? 1.333 should be 1.333, okay? For the A side should be 1.4. Gas side is 1.333. CPG is 1.11, the gas side, because your turbine work is on the gas side. So make sure your CPG, you use the correct value. Don't use the 1.005. So 1.11. So you got your work output. Okay. So on the tail is 3 and 4 prime, not 3 and 4. Yeah? If 3 and 4, that means you are looking at closed gas turbine unit. So this, I have listed out all the temperatures. I have listed out all the temperatures which we have found and given, so that it makes our things much easier. It makes our working much easier. Okay. So work in, that is the compressor, CPA, the A side. We are taking 2 prime and 1. So CPA T minus T1. You can also use instead of CPT, you can also use instead of CPT, you can use change of H enthalpy, because I repeat once more, H is CPT. So you have this. Now how H is related to CPT, that you have to study in other chapters, which we call general relationship for thermodynamics properties. So for CPA is 1.005. T2 prime 614, which we have found. 288 is given. So you'll be able to find out the work in. Of course, we need work in, work out, and heat supply. Okay. So the net work out, we know that the net out will be equals to mechanical efficiency. This term here, recently, okay, we have not looked into this term. This term here usually used when you have any shaft work involved. So usually the gas turbine is used to drive the air compressor and the generator. So there will be power transmission loss due to friction. So that is why there will be a mechanical efficiency sometimes which is being introduced. If there are no mechanical efficiency stated, then we can assume this is 100% effective power transmission. 100% effective power transmission. So that means there's no loss due to friction. Okay, if there's a loss due to friction, let's say 2%, then your mechanical efficiency will be 98%. If there are loss of due to friction, power transmission due to friction of, let's say, 4%, then your mechanical efficiency will be 96%. So you will have to take your net work multiplied by mechanical efficiency of 0.96 or 0.98 or whatsoever. So if the question doesn't mention or doesn't give us, doesn't state that to involve mechanical efficiency, usually we take it as 100%. In actual practice, it won't be 100%. Okay, so we get our network out. In the next question, we will have something that is where we will be introducing the mechanical efficiency. So power net, m dot times work net. So you got m dot is given in the question, 15 kg per second. Okay, so the power, which is kilowatt, which is also kilojoules per second. So you have this as kilojoules per kg. Multiply this with kg per second. So that is why you have kilojoules per second here. That's for power. Net power output. So the heat supply, remember, combustor is in the gas side. So that is why we use CPG here. And it's the difference between 3 and 2 prime, not 3 and 2, yeah? 3 and 2 prime. You have to look at the diagram. Because certain diagrams that give you this 2 prime, this as 2, then you will have to take T3 minus T2. Okay? So that's supply. So cycle efficiency, remember, that is net work out over heat supply. So you've got a cycle efficiency as 18.38%, which is very, very low. So that is why a simple gas turbine unit, usually we use to combine it with a vapor power plant. Okay? Combine, which we call it as combined power plant. Those we call as combined power plants. Okay, so gross work. So we know gross work is based on all the expansion work. So only turbines. So we say gross, that means if let's say you have 3 turbines or 2 turbines, you have to add up all the turbine works to give you the gross work expansion. I mean the gross work. So this will be 401.563, which is the work output of the turbine. So the work ratio usually is defined as net work out over gross work expansion. So you can see the work ratio is super low. That is only 0.18. Okay. So I hope this is helpful. And I would like to say thank you and see you in the next video. Bye for now. Take care. Stay safe.